Hello again, this is the presentation for the second lab, and we are the group formed by Marc, Pérez, Xavier, Akira, and Abril. Regarding the section 1.3, it asked us to compare it with section 1.2 and how section 1.3 has improved from that one. In section 1.2, we generate the weight vector with a set of random values, and we do not treat that weight vector. We actually just use it as is. That is why we end up with this flat line in the plot. However, in section 1.3, the model goes to the descenso gradiente function, meaning that iteration after iteration, we get a better fit for the model, and we go updating the weight vector. Regarding the chart tracking the weight vector evolution, we can see that it goes from practically zero and it spikes in order to better predict the dataset. And then it slowly goes down to the values that we entered at the beginning, which are roughly 40 and 6. So yes, we can say that the weights end up being close to the real values of the data. And we can see this improvement in the error plot, which flattens at around iteration number 8 or 9, meaning that the error is minimal at this point. Now on to section 1.4, in which we have to compare the training dataset to the validation dataset. In here we can see that the plots of the error basically mimic each other because we're using a very big dataset. So no, they do not seem to diverge in any iteration. However, using a smaller dataset, we will see obviously some errors because the differences are much more relevant.
All right, for section 1.5, we are said that if we find a better solution when providing more samples, we think that we're not providing a much better solution. It can be a bit better, but not that much. We can observe that the error gets stabilized a bit faster than having the samples, meaning that it will converge faster. Here it converges a bit before than when with less samples, but not that much. And when having less samples, this will lead to more error in the training algorithm, but both having more or less samples will converge at some point. Here we're having much more error than before with less samples, but the tending is that it will tend to converge in some point also with less, more, and more samples. Section 1.6, no, the linear model will not fit the nonlinear dataset since the data points here show a sinusoidal shape. You can observe here with my mouse, but the line stays straight horizontally, and this is not accurate approach of our dataset. This is not surprising since we will need to make a use of a nonlinear model algorithm to approach these points in the dataset. And here,
due to the nonlinearity of the input data, we can see that the model comes up with a very poor fit. Since it only operates with linear weight relations, it can only describe the data in its broadest terms, so as best as it can. Therefore, the bias term that it comes up with is 0, and the weight term is also very, very close to 0. We can see that the bias is, in a sense, correct because we know the true offset of the function to be 0, but the weight term is very wrong, obviously, because it's unable to account for the true sinusoidal variation in the data. We can also note that the error function converges to a value that's close to 0, but that's only because the data points located at either side of the regression line cancel each other out. By just looking at the spread of the data, we can easily infer that the relationship between the two variables is linear, with the two quantities being positively correlated. And then after performing the gradient descent, we can see that this is the case, as it's able to come up with a solution of W0 equals minus 3.6 and 1.2 for the weight term. Therefore, we can confidently extrapolate to infer that a store placed in a city with 100,000 inhabitants will be approximately $120,000 less profitable than if it were in a city with double that population.